Get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's get into it. If you can turn your cameras on, that would be appreciated. And of course, participate. There's going to be a group participation part of this class. So hopefully you guys are ready for that and you know who your group members are. I think in this class, we only have 2 groups, very small class. So let's continue.
Recording in progress.
Share screen. Okay, so make sure I can see the chat. There we are. So let's do a quick recap of what we did last time. We started talking about linear inequalities, and we're going to extend that today to systems of linear inequalities. So just to remind you, a linear inequality is just something that can be written in one of these 4 forms. So ax plus by greater than c, less than c, greater than or equal to c, less than or equal to c. And yeah. Now, what does it mean to solve one of these guys is that you want to find all the points, the coordinates, x comma y, that make those inequalities true. So you want to plug in x and y values into each of these, and you'll get a statement, right? So I can plug in x equals 1 and y equals 3, and then I would be able to, it will make a statement, maybe like, oh, 5 is greater than 11. And then I will say, oh, that's false statement, which means 1 comma 3 is not in the solution, right? So we want all points that make these statements true. We call that the solution. Now we graphed the solution in last class. We learned how to figure that out by shading, right? So to graph the solution, first you sketch the line. You pretend the inequality was actually an inequality. You sketch the line. If it was a strict inequality, it's a broken line. If it's a non-strict inequality, you do a solid line. Then you'd realize that that line is going to cut space into 2 parts, like a left and a right, or a top and a bottom. And you pick a random point in one of them with very easy numbers to plug in, and you test it in the inequality. And if the inequality makes sense for those numbers that you plug in, then that coordinate is included, and literally everyone in that half plane is also included. So you shade that entire half. If that inequality is not true, then it means that people in the other side form the solution. So you can shade the other half. And so that's how you went about doing that. You could also just isolate the x or the y. And based on how the inequality looks, you will know whether you shade above or below or to the left or to the right. Sometimes inequalities can be given to you in one of these forms. And so it's convenient to just do this instead of doing any computations and plugging stuff in. Okay, so the shaded region represents the graphical solution, right? So that's all coordinates in the blue shaded region here will solve my inequality. So that's what we got. And I left you guys with some examples to try last time. So that's what we're going to do now. So we are moving into systems of linear inequalities. Okay, so in the last episode, these are the enemies our heroes are faced with. And this is just me copying the examples from the last class here and kind of minimizing them. But before we get into that, a word from our sponsors. Let's need to talk about some definitions and processes here so far. So let's actually get into that first. Okay, so we're in 5.2 now, systems of linear inequalities. So let's talk about what those are, how we're going to do it. You should have tried it already, but let's make the formal definition because last time I said most things verbally. So definition. A system of linear inequalities is a set of, and we'll talk about sets in a little bit more detail later, actually, of linear inequalities that are considered together. Okay, now the solution to the system is the set of all points x comma y that satisfy all the inequalities simultaneously. Parenthetical statement, it's possible for there to be no solution. So example, if I say, oh, here's my system of linear inequalities, x is strictly bigger than 1 and x is strictly less than 1. That's my system. That has no solution, right? There are no set of points that could fulfill both of these requirements at the same time, right? So yeah. So it's possible for there not to be a solution. But of course, a lot of times there are, and in the situations that I'll be talking about and asking you about, there will be, right? So, but that would be the system. That would be how you find the solution. You just want the region in space. The graphical solution is the region in space. The guy we found by shading last time. Is the region in space that solves all the inequalities. It is the intersection of the solutions of each inequality present. If it exists. Right? So essentially it's going to be an overlap of all the solutions that I taught you guys how to find in the last class. You're going to have to find several solutions and kind of overlap them. The solution region in this case is called the feasible region. So this is what we call it whenever we're talking about systems of linear inequalities. And someone says, find the feasible region. It's really like a solution set, but it's the solution set that satisfies all inequalities at the same time, right? So that's called a feasible region, right? So now, oh, still need more space. We're not going to get into the examples just yet, but I can probably, can I fit it? So let's talk about the process for finding the feasible region. One, sketch all inequalities. On the same axes. Two, find the solution to each 3, find where, if anywhere, all the solution regions overlap. And I'm going to tell you how to actually do that now. So let's go. All right, so we're going to do these examples. Guys, I had you try for last time. Hopefully you did try it, but let's actually discuss them. So let me move that over in the corner there. We don't need that yet. So here is a possible system that you might have to deal with, and we want to sketch the feasible region for this system. So that's the guy we're dealing with.
Would you be able to scroll up to the process one more time so I could take a picture?
Oh, yeah. So you sketch it, you find the solution. So parts 1 and 2, I taught you how to do last class. Now part 3 just comes down to you figuring out the overlap of all of these situations.
All right, thank you.
So yeah, now we can get into it. So here's the first example. So this is a system, relatively small system, relatively simple system of 3 inequalities, and we're going to find the feasible region. So what do? Well, we saw how to kind of deal with this last time. So we will start by actually trying to sketch what's going on. So we first want to sketch x plus y is less than 2. We saw how to do this. You only need 2 lines to sketch a linear inequality at most. And pretty much you plug in one variable equals 0 at a time, solve for the other guy. Plug in x equals 0, you get y equals 2. Plug in y equals 0, you get x equals 2. So you know it intersects on 2 and 2. So your line is going to look like so it's going to meet here at 2, and it's going to meet there at 2. Now, x greater than 0, well, that's going to be the y-axis. If you sketch x equals 0, so that's what I sketch in blue. It's this guy. This was the guy I sketched in red. Right? And then y equals 0, that's just the x-axis. So that's this guy. Okay. Now, these are the y and x axis respectively. We don't have to sketch these. On top of the axes we already drew. I did it here for emphasis. Right, so you're already going to have these guys sketched because you sketched the axes. So you don't have to sketch a line on top of the line that you already sketched. I'm not even going to notice it anyway. So I'm just sketching it here. You can do it in a different color, and you can see that what in my mind are the important things to look for. So yeah, you sketch those 3 guys. And now, like I said, you're just going to find the solution for each of these. Now, there are a couple ways you can do this. One way to proceed it's actually not the recommended way. And I'm going to explain why it's not recommended. So you might say, why am I showing you this if it's not recommended that you do it this way? Because it's going to illustrate the process of finding the solution that I want to get across. But at the same time, in practice, it's kind of not very, it's not the thing you want to do, but it's going to be very instructive if I do it this way so that you can see, oh, that's what he's talking about. So I'm going to do it this way just so you can see what is the process of actually finding it. But in practice, you would actually do something slightly different. And I'm going to, I'll show you that right after. In fact, let me copy this guy so that, in fact, I should probably do something else. It's going to be, when you're dealing with multiple things like this, you're definitely going to want to label them. So let me make sure this here is x equals 0. This here is y equals 0. And this here is a line x plus y equals 2. Right? So you're going to want to label them. You're going to realize why that's important later on. But you do need to know where all your boundaries are, which line represents what boundary, because sometimes you're going to have multiple lines and you're going to need to know quickly who is this line representing, right? So yeah, so I'm going to do here. Just copy that. So we're going to actually do that in a couple ways. Okay. So one way to proceed is to actually shade all solutions and find the overlap. Okay, so what does that mean? Well, the same thing we did last time. So let's focus on the red line. What are the solutions for the red line? Well, we saw how to do that last time. You plug in a random coordinate. In this case, let's plug in the origin x equals 0, y equals 0. Now, if I plug in x and y equals 0, I get 0 less than 2. This is a true statement, which means the origin is included in the solution, which means everyone below that line is included in this solution. So this is the solution for the red line. Not sure why it does that. Right. Then for the green line, that's the y equals 0. I want y greater than or equal to 0. So obviously the solution for that is everyone above that line. And for the blue line, I want x greater than or equal to 0. So it's everyone to the right of that line. So here you can realize where all of these guys actually overlap. It's actually this little triangle right here. Is where everyone actually fits together. Hold on. Or everyone is satisfied at the same time in that overlapping region. Can move this down a little more. Okay. So here we see the feasible region is it's the region that essentially looks like this. Blue that way, red this way, and green that way. Where all the shadings overlap. Okay, now, so question, how do we determine which way to shade? Again, there are two ways. Either, well, I mean, That was in last class. Either you test a random point, you pick a random coordinate, you plug it into the inequality, see if it's true. If it's true, you shade that half of the line. If it's not true, shade the other half. Or you rewrite it by isolating the x or the y, and based on how it looks, you would shade either above the line or below the line or to the left of the line or to the right of the line. So for example, we had y greater than or equal to 0 in one of those things. That looks like this part, which means I want to shade above the y greater than or equal to 0 line, which is why I shaded the green going above, right? So we can do that, or we can plug in a coordinate. So for the x plus y less than 2, I plugged in a random coordinate. I plugged in the origin, 0, 0. If I plug in 0, 0, I get 0 is less than 2. That's a true statement, which means the origin is included. So everyone on the same side as the origin is included. So I have to shade up below the red line. Right? And you do this process over and over repeatedly for every inequality that occurs. And you shade where they exhibit their solution. Now, here you can see the feasible regions where all solutions overlap. Now, the reason why I say this is not recommended, this can get confusing if you have many inequalities, right? Right? So if I give you a system with like, there's 7 of these guys, 7 lines, you are now going to want to find the region where all these 7 different shadings that you did overlap, right? And it's easy to mix that up with a region where only 6 of them overlap. Like you're barely going to be able to tell the difference. You're going to end up picking the wrong region because of that. So there is a possibility of confusion in using this method, but it illustrates what we're actually trying to accomplish. It's just where all the solutions overlap that's the region that we want, right? So here the feasible region is that, and it's indicated by that triangle, the boundary is, the triangle part. Okay, so everything inside that is going to be your solution region, or what we call the feasible region. Okay, so that's the feasible region. That's how we found it. Now, another way is to actually to proceed, probably the recommended way, is to use arrows. Is typically what people use. In this case, I will make them pink arrows to indicate the direction in which you would shade. But you don't shade anything but the feasible region in the end. Okay, so what would that mean? So I go here and I know that, oh, I want x plus y less than 2. Plug in the origin, 0 is less than 2. That's true. The origin is in my solution, which means I know I want to shade below or to the left of the red line. But I'm not going to do that because I don't want to confuse myself. So what I'm going to do instead is put arrows on the red line that indicate to me what direction I would shade in when I'm ready to shade. So I just draw two little arrows on the line. Similarly, I'm going to know that I want to shade above the green line, and I want to shade to the right of the blue line. Now, by telling me, these arrows kind of tell me, okay, this green line, you should be above that. So I ignore everything that's below that. Oh, this blue line should be everything to the right of that. So I ignore in my mind's eye everything to the right of that. So now my focus is on the first quadrant. Then the pink arrow on the red line tells me, oh, you should be below this red line. So now I zone into that, oh, the shading is in the triangle right here, right? So now I only have to shade that, right? So, feasible region. Right? And there's not all these different types of shading that I have to figure out. Is all of them here? Like I don't know. I don't care because I never started to shade until I knew what I wanted to shade. Right? The arrows just kind of told my eyes where do I look, right? And once I'm looking in some position where it violates one of the arrows, then I know I don't shade it. So if my eyeballs hit over here, I'd realize, well, that violates this arrow because I should be looking on that side, right? So I know the solution is not over there. I'm not going to shade it, right? So yeah, those are the two ways, two main ways, which the second one is more recommended, I would say, to determine the feasible region. Any questions on this so far? Is anyone alive? Are we alive out there? I don't know.
Can I get the first one more time, please?
The first one is in the first method.
Yes.
Yeah, so that one you just shade the solutions for all of them individually. And of course, you probably want to shade in like a different pattern so that you know how to identify which shading goes for which person. And then you just take the overlap of all the shadings, right? Which can get confusing, but it does illustrate the idea of what you're heading for.
Yeah, why is that one not recommended compared to the arrow one?
Yeah, like I said, if you have a lot of these things, it starts to get confusing, right? Like if I had several, let's say I gave you 7 or 8 different inequalities, right? You're going to have to come up with 7 or 8 different shadings where your eye can know, oh, this shading relates to this guy. And then you're going to have to figure out what region do all 7 shadings overlap in, right? Which it's not going to look much different from a region where 6 of them overlap, right? Versus 7, right? Eventually it gets confusing for your brain to keep track of all the shadings, right? I mean, you can do this if you only have like 3 or 4 guys, but if you have many of them and you have all these shadings all over the place, by the time you try to get to where the answer should be, there's too many shadings around it. It gets confusing. So here in the second method, you don't shade until you already know where the answer is, right? So like there's only one thing to shade here. It's definitely clear, unambiguously, that what's inside that right triangle is the solution. And it doesn't matter if I had 3 lines or 15 lines, I would still be obvious. The solution, the feasible region would still be obvious, right? I won't have to count, oh, yeah, in this region, only 14 overlap. Okay, let's count in this region. 8 of them overlap. Okay, not good enough. This region, 13 of them overlap. Okay, this region, oh, all 15 overlap here. Like you're gonna have to be counting, like it can get crazy, you know? So that's what I'm saying. When you're a human being doing this by hand, it can get crazy. If you're a computer, it wouldn't matter, but we're not computers. You have to be aware that your human brain has so much working memory, can only keep so many things in RAM at a time. So yeah, those are the 2 main methods. There's like a smudge here. But so far, do we kind of get what we're doing? We're okay now. Those all the questions?
Yes.
Okay. So yeah, so that's that. Now here's the other example. So let's say B. So that was example A. Let's do example B. This one should be a little quicker because we already kind of know. And it's actually, let's not copy, let's cut. And it's actually very similar to example A, actually. I'm going to need more space. And this is the other example we're going to do. Okay, so here's B. Yeah, you'll notice that this is actually very, very, very similar to the last example, except where I had less than 2, I now have greater than 2. So what's going to be the difference in this system? Right, so I just want to modify the other example a bit because, like I said, your brain only can keep so much in mind at a time. So you want to make sure, and this is kind of a pro tip. Of course, I'm doing this because I'm teaching and I know how the brain works and that's why I'm doing it this way. But this is just as a lesson to you when you're studying, for example. You want to set things up in such a way that you don't have to keep a lot of things in random access memory or your working memory at a time. You don't have to keep too many things. So because I already know you guys know how to sketch the lines involved in this problem, if I want to show you a different concept, I'm going to just give you a problem with all the same lines. So now your brain doesn't have to worry about figuring out those lines again. It already knows it. And so you can now focus on the other thing that I'm trying to get at. So we already know what the lines are going to look like. So let me just graph those. Right. And like I said, you don't have to sketch on the axes themselves. We kind of know where those guys are going to be. Now we're going to do those arrows. I want to be greater than 2. If you plug in the origin this time, plug in x and y equals 0, you'll realize that the first line says that 0 is greater than 2. That's not true, which means the origin is not included, which means I want to be above this red line. So this time, I want to look in that direction. Then I know I want my x to be greater than or equal to 0, so I need to be above this line. And I want my, that's my y is greater than or equal to 0. And for my x greater than or equal to 0, I need to be to the right of that line. So I know I should be looking on top of the horizontal axis to the right of the vertical axis. And then according to this red line, I should be looking to the upper right of that red line. So that tells me the feasible region is over here. No. That tells me the feasible region is over here. Okay. That's the feasible region. Okay, so that's the solution to this system of inequalities, right? Yeah. So there was nothing new to explain there. I'm just kind of going over all the things I already spoke about. So I know, hopefully that's clear. But these two examples do bring into consideration another thing that's going to be important. So that's also something I want to emphasize. Bounded and unbounded feasible regions. Okay, so Definition. A feasible region is called bounded if it is possible to draw a circle of finite radius centered at the origin that encloses the entire region. Otherwise, it is called unbounded. So that brings up what we had in the examples above. So you'll notice here in the above, for example, A, we had something that looks like this. Feasible region was inside here, right? Now notice what that actually means is that it's possible that I could have drawn a circle where, let's say, it centers right here. And what I can do is I can center that circle at the origin in such a way that, notice, the entire shaded region fits inside of that circle, right? So this circle encloses the entire feasible region. So here, the feasible region is bounded in this case. Now, if we look at the second example I did for you guys, still had the same situation going on, still had the same feasible region going on. No, not the same feasible region. Our feasible region in this case was above here. Now what you'll notice is that no matter how big I draw a circle, it's going to miss some of the shadings. There's going to be some shading in the far top right that cannot be included in any circle that I draw. So any circle that I draw is going to miss some of the shading. So the feasible region is unbounded in this case. Okay. So basically what that means is the coordinates that solve the system, the magnitude of those coordinates go off to infinity, like they're unbounded. I can't bound them in anything. They just go off without bound. Okay. So it's an unbounded feasible region. So that's going to be something that comes up to be important later. So for now, let's not worry about it. But eventually there's going to be a theorem that we're going to want to use that it depends on the region being bounded or not. But now what we're going to do is this example, or more specifically, what you guys are going to do is this example. I'm going to put you guys into breakout rooms. You're going to work on this, and you're going to come back and just tell me the answer. So that's what we're going to do. So
which example is it? C?
no, there are 4 different examples here. So I'm going to tell
okay.
you which ones to work on. So since we have 4, and I think this class I broke into 2 groups, I'll just actually assign them at random this time. So I'm going to break you guys into 2 groups. And yeah, so what I want you to do is whoever was assigned to room 1, do example A. Whoever was assigned to room 2, do example B. And if both of you guys finish that early, I'll give you guys 5 minutes to do this and then pull you back. Whoever finished that early, you guys can try example E, as in the last one. So yeah, all rooms are open. I will see you guys in a bit. Okay, everyone's back. So let's just talk about what the answer would be, and then I will let you guys go. So hopefully you got this, your picture looks something like this, right? The blue and the red lines. Ignore all the Roman numerals in the bubbles. Do you guys get something that looks like that? Okay, so now, based on the problem that you attacked, different people would shade different regions. So what I decided to do was to number the regions. And what you can do is, for your group, you can tell me which regions were shaded in your solution. So like group 1, so you did that first one. What regions were shaded? They're labeled in Roman numerals.
I got 5. 5 was my or like the region that had every line shaded in it.
5?
Yeah.
5 is here.
No, heck. Oh shoot, my bad. I'm not a Roman numeral.
Oh yeah, that's the next. This
Yeah,
one?
next.
Yeah, that's 10. That's region 10. Yeah. Okay.
I got
And that's
I
the
got
only
10
one.
as well.
Yeah, that was the
So-
only one that had all of them.
Okay, so we think that this was the answer to A. Okay. The people that did B, what regions were shaded for you?
So I was able to plot all that, and then I plugged in random numbers to the first 2 equations because I understand the second 2, and I found that they were incorrect. I just don't know what that means in terms of the shading. I forget. So like I put 1, 1 into both of them, and they were incorrect. So would it go above the 2 lines? So maybe 1.
Yeah, so that's what I meant with this thing.
With the
You don't do both at the same time. You do one at a time.
yeah, I did.
Yeah, so you want to find which one at a time, who gets satisfied by what. So where would 1, 1 be then? 1, 1 would be down here somewhere, right? In region 10.
Yeah, so it doesn't work.
Which, yeah, so you know that region 10 and nothing below that is going to work. So you had to test the other regions.
Oh, okay, got it. So we know. Okay, then can I have a moment real quick to plug in other numbers?
No, because we're going to end. So we will pick up with these next class.
Okay.
And before we jump into the next section, but this is all that we need for 5.2. But we're already like a few minutes over time, so I don't want to actually do anything more. But yeah, finish it up now that you know that. So you pretty much want to identify what region works. And again, I would say now you're starting to realize, because there's so many places to figure out what works, plugging in points and shading each and going with essentially what you're trying to do, method 1, gets confusing. If you were to just on each line draw the arrows in which direction you should be shading, the answer is going to be obvious, like almost right away. You're going to know, oh, it's this region up here. Right. So, I mean, if you did the plugin method, what you did plugged in 1, 1 first, then you would just happen to get lucky because region 10 happens to be where the solution is. And so you'd have plugged in the point that happens to be the right answer. But there are 10 possible positions that the answer could be in. And you're going to have to figure out all of them. So it's much better if you just put the arrows will point you in the direction where the answer should be. So you would know if I have arrows pointing away from region 10, I'm not even going to test region 10. I don't care because I should be looking up here, right? So that's the benefit of this method. But with that being said, I think we'll end there. So try that again for next time, and we'll pick up with that, and we will actually go beyond that. So now that we know how to do this, we're going to be able to do what we actually want to do, which is linear programming. So we're going to get problems that are word problems that drawing these pictures is going to help us get to those answers. So that should be interesting. And I'll also teach you guys how to solve these guys on computer, in Excel, and Python. So that should be interesting for next week as well. That being said, thank you for your attention. I'm going to let you guys go, and I will see you guys in the next one.